Good evening, everyone. Welcome to the live session number 11 for Polymer Reaction Engineering. We will be discussing some sample problems so that it will be helpful for you in solving this week's assignments. Start. In today's session, we'll be learning about ionic polymerization process and the parameters which are. So starting from the first question, we have steady state assumption in slow cationic polymerization is only valid if the options are the rate of initiation when it's less than rate of termination, initiation greater than termination, and initiation greater than propagation, and rate of propagation is constant with the conversion. So during steady state assumptions, there are certain parameters which need to be studied. So there are instances when reactions proceed too rapidly. So, because ionic polymerization process occurs even more faster than radical polymerization process, as we have seen in the previous lectures. So, there might be instances when the reaction proceeds too quickly, and because of that, no steady state is achieved. And then, in the next case, when the rate of initiation is greater than that of rate of termination, in that case, what happens is concentration of propagating centers slowly increases throughout the polymerization process. So what happens in this is that it reaches a maximum rate in the reaction. So steady state is not reached till later in the reaction, and then again it starts decreasing. So because of that, rate of initiation should be lower than that of rate of termination. So in that case, option one would be correct. Other scenarios include that when rate of propagation is constant with the conversion, in that case, what happens is since propagation is constant with conversion, there is no net change. So in that case, steady state is again achieved. So that's why rate of propagation is constant with conversion is another condition which satisfies the steady state assumption. Uh, but for rate of propagation when it's constant with conversion, there are some exceptions during which like it does not consider when monomer decrease or the initiator concentration decreases. So that case is not considered. So without that rate of propagation, when it's constant with the rate of conversion, steady state assumption is valid. Moving on to the next question. Protonic or Bronsted acids initiate cationic polymerization by protonation of the olefin. The anion of the acid should not be highly nucleophilic, otherwise it will terminate the protonated olefin by combination. So it's a true or false question. So protonic or Bronsted acids, they are used in initiation of cationic polymerization processes by protonation reaction. So, for example, if we have a like this, if you have attended the lectures, you would know this reaction. And we have a species right here. On dash minus. So, uh, attached with the small. So, when protonic or Bronsted acids initiate the cationic reaction, what happens in this case is that the uh, this double bond gets broken up, and because of that, the you can see the resultant intermediate will be something like this. Since the double bond is breaking right here, we will have a special carbon right here with a positive charge on it. In the CH2 group, CH3 group forming the methyl group right here. In the H A breaks up, and then the A acid group will attach right here with a negative charge. So in this case, protonic bronze-state acids do initiate the cationic polymerization, the protonation of the olefins. So you can see the protonation reaction right here. So this is true. In the next statement, we have the anion of that acid should not be highly nucleophilic. So nucleophilic species are usually deficient of electrons. So in that case, if it's highly nucleophilic, what will happen is that it will terminate the reaction immediately as it will accept the electrons, and the A group right here, A negative group, will stabilize and it will terminate the reaction. So this statement, the entire statement and both its parts are true. Moving on. For a compound to act as a cationic initiator in ionic polymerization, it should be, here are the four options: uh, highly nucleophilic, less nucleophilic, electrophilic, or highly electrophilic or less electrophilic. So in cationic initiation process, if you have a excessively nucleophilic, highly nucleophilic compound right there, it will limit the utility of the most of the strong acids as cationic initiators. So it is going to limit high nucleophilicity will limit the initiation power of strong acids. So in that case, it should be less nucleophilic. Moreover, for example, like hydrogen halides are ineffective as initiators of cationic polymerization because they have the halide group. Halide groups are very highly nucleophilic, which which totally inhibit the initiation process, and hydrogen halides fail as cationic initiators in that case. So the next question we have, for a compound to act as a good cationic polymerization initiator, the following properties are required. Choose the correct option. It should be highly nucleophilic compound. It should be a strong acid, example hydrogen fluoride. So just in the previous questions, we saw that highly nucleophilic compounds do not act as good cationic initiators. And similarly, we saw that hydrogen halide, any halide, then that would be hydrogen fluoride, are ineffective as initiators during cationic polymerization process. So we can eliminate the first two options. Next, we have the electroinitiation process. It's a possible way where either monomer, solvent, or electrolyte or any other added species can initiate the process. So electrolytic or electro-initiated polymerization, it involves initiation by cations formed via electrolysis of some of the component of the reactant system, which can be either monomer, solvent, or electrolyte. So when these monomers, solvents, or electrolytes undergo electrolysis, the uh, charged molecules which are formed will help in initiation of the reaction, cationic polymerization process. So that can be used as an initiator to start a reaction. So that's why electroinitiation process is the correct answer. Moving on. Generally, the amount of energy required to ionize the neutral molecules per unit mole to start ionic polymerization is. This is a pretty straightforward question. If you have seen the lectures, you know, and if you have seen any kind of ionization process, that it requires very high amount of energy to ionize any kind of molecule. So, and that's why you can directly choose the upper threshold limit right here, that is 9 electron volt or more. This is usually achieved by radiolysis or photolysis. And in both cases, radiation is required to achieve high energies, which will be required for ionization of any neutral molecules. The ionophores, which binds to a particular ion and shield its charge from hydrophobic environment of the membrane, forming a lipid-soluble complex of cation which then diffuses across the membrane, are classified. We have two options here: mobile carrier ionophores and channel forming ionophores. So, mobile carrier ionophores, what they do is they bind to a particular ion and they shield its charge from any kind of hydrophobic environment. Any kind of hydrophobic environment close to the membrane. So because of that, uh, reversibly and by reversibly binding to the ion, it helps to form the lipid soluble complexes, which then diffuse across the membrane. It is actually th- they can catalyze passive transfer of cations across the hydrophobic membrane also. So because of that, mobile carrier ionophores are classified according to this. So the correct answer for this question would be the mobile carrier ionophores. Whereas the channel forming ionophores, they introduce the hydrophilic cores into the membrane, using the specific cations to pass through without coming into contact with the interior of the membrane. So in that case, lipid soluble complexes can be made. So that's why mobile carrier ionophores are the ones which are responsible for formation of lipid soluble complexes which rapidly diffuse across the membranes. Next question we have. What are the conditions required for achieving a narrow molecular weight distribution polymer during ionic polymerization process? So the options we have: high chain transfer rates, low termination rates, rate of initiation should be equal to rate of propagation, and Olympic. So if you look at the all options, what, what is desired is having a narrow molecular weight polymer distribution. So during ionic polymerization process, having a high chain transfer rate would be very unfavorable because chain transfer process basically halts the activity of a polymer chain and then passes it on to the other molecule. So that would be very undesirable for getting a uh, polymer with a narrow molecular weight distribution because high transfer rates are undesirable. Then next we have low termination rates. Low termination rates are very favorable because since having low termination of the chains would result in formation of long chain molecules, and if all monomers polymerize to high chain lengths, that would give us a narrow molecular weight distribution. Rate of initiation should be equivalent to rate of propagation. In this scenario, what would happen is rate of initiation when it's equivalent to rate of propagation, uh, as we have seen in the beginning, that steady state would be achieved, and then the polymerization process would would be constant. And in that case, nanomolecular weight distribution polymers will keep forming till the process terminates, or decreased monomer concentration or initiator concentration is occurred. So in that case, second and third option are the correct answer. Moving on, we have which of the following can be used as experimental methods for determination of the absolute rates, absolute reaction rates for polymerization process. So amongst these, uh, let's take a look at all the options. First is the short stopping of polymerization system. In short stopping, what happens is you uh, introduce a very strong terminating agent to stop the formation of the polymers. and to halt the polymerization process. This this kind of experimental method is limited by the general difficulty of the end group analysis, since the concentration of end group analysis can be low. So because of that, the this experimental method is used, but not that widely, and it is despite its shortcomings, it is one of the experimental methods which is used for determination of absolute rates. Next one we have UV visible spectroscopy. In UV visible spectroscopy, what we are saying is that we are basically seeing this spectroscopic analysis of the propagating species during the polymerization process, where the high extinction coefficient of the aromatic mm, carbon carbonate carbocations propagating species are observed. So because of that, absolute rate determination can be very feasible. On top of that, the absorbance, UV absorbance of the system as a function of time allows us to determine the initiation rate constants and the propagating species rate constants also. So because of that, UV visible spectroscopy and short stopping of polymerizing system are used as the experimental methods. And the final one is the addition of chain transfer agent to the polymerization reaction. Addition of chain transfer agent to the polymerization reaction would disrupt the polymerization reaction, first of all, which cannot be used for measuring the absolute rate constants during the reaction. So, because since chain transfer process will only halt the process, only halt and pass on the growth of a single monomer onto the next molecule. Because of that, the addition of chain transfer agent to the polymerization reaction would not result, it would not give the correct determination of the absolute rate constants. What physiological changes occur in cells due to the electrochemical gradients caused by the ion force? Now, what happens in cells when electrochemical gradients are formed? If you have read the lecture notes properly, you would see that this is a general question. It shows that when the cell walls and the osmotic balance is disturbed whenever the electrochemical gradient is generated by the ionophores. On top of that, the cell signaling changes, which is a physiological feature. On top of that, oxidative phosphorylation also occurs. So all of these processes occur whenever there is a change in the electrochemical gradient caused by the ionophores. Uh, we have the final question. Which factors can cause the changes due to the effects of reaction medium? Now, cationic polymerization process is actually very much reaction medium sensitive. So amongst these, we have a counter ions, solvents, and chain transfer agents. So the, what what brings these changes is that what is the effect of these changes is that the equilibrium between free ions and ion pairs is shifted towards free ions due to high polarity solvents. So affect solvents pose an effect on the reaction medium because of which it disrupts the cationic polymerization process. On top of that, uh, it increases the polymerization rates, which can be caused by agents, counter ions. On top of that, whenever low polar solvents are encountered during the polymerization process, low polar solvents drive the reaction system towards the formation of covalent species, which does not propagate or they propagate more slowly than the free ions, because of which the counter ions and solvents affect the reaction mechanisms. Whereas chain transfer agents do not have chain transfer agents result in termination of the reaction itself, and The reaction medium itself is not affected. So because of that, it does not have a significant effect through the reaction medium onto the factors which cause the polymerization process to change. So counter ions and solvents, the correct. I hope you solved all these questions and have gone through all the lecture notes because this is the final week and you will be giving your written tests in next week. So we'll be having a summary class where I'll be discussing some questions and some concepts where we'll see whatever we have learned from the first class. Thank you.